Okay, so let's move to the fourth atomic diffusion mechanism entitled interstitial C mechanism. Based on the name interstitial C mechanism, for sure it is something related with interstitial defect, right? So it's a little bit similar with what we show you interstitial diffusion mechanism, and also something different, but it's for sure is related to interstitial defect. So let's introduce to you what's the interstitial C mechanism. The diffusing atom jump between substitutional site and interstitial site by following a two-steps process. The first one is the atom at the substitutional site exchange with an interstitial defect. And the second will be the atom in the interstitial defect exchange the location with the atom at a substitutional site. Briefly say, actually the atom jump between substitutional site and interstitial site. So if I use this figure as an example, here we can see that the host atoms, right? And we use the gray ball or gray circle to represent the diffusing atoms. And now we use the blue circle to label the atoms at the interstitial site. But don't forget, this atom is the same atom with our host atom, okay? So it's not the smaller solute atom we introduced to you in interstitial diffusion mechanism. This size and the type of atom are the same with host atom. So we have self-interstitial defect happen in our materials. So now in the beginning, you can see that the number 3 atom locate at interstitial site. Then number 3 push number 2 atom number 2. So now the number 3 locate at substitutional site, but the number 2 atom be pushed away to interstitial site. The next step, we find that the number 2 atom push number B atom, which is a diffusion atom. So the number 2 atom jump from interstitial site to substitutional site, but however, diffusing atom B moved from substitutional site to interstitial site. The next step, we find that diffusing atom B push number 4 atom, so the diffusing atom B jump from interstitial site to substitutional site, then the number 4 atom jump from substitutional site to interstitial site. So the number 4 atom at the interstitial site push the number 5 atom move away from substitutional site to interstitial site. So you can see in this case, the atoms jump interstitial site to substitutional site, interstitial site to substitutional site, jump back and forth. And after diffusion time, you can see the diffusion atom B diffuse, right? So this kind of atomic diffusion mechanism, we call it as an interstitial C mechanism. There are some criteria and some key points can help you to determine whether the case you deal with belongs to interstitial C mechanism or not. Based on the series example, you know that for sure there's a presence of a self-interstitial defect. Self-interstitial defect, the term means that the atom located at the interstitial site is the same type and size of atom, the same type and size of the atom as our host atom. They are the same type of atom. So but just the atom at the interstitial site. So under this situation, this we also call it as a self-interstitial defect, because the host atom locate at interstitial site, so we call it a self-interstitial defect. So this diffusion mechanism actually is driven by the diffusing the self-interstitial atom nearby the diffusing atom. So that will drive the interstitial C mechanism. So let's the other type of diffusion mechanism you learned before is some kind of similar with this one, which is the vacancy mediated diffusion mechanism. The diffusing atom, the mechanism actually is for sure there's a vacancy nearby the diffusing atom, right? But here is a self-interstitial defect nearby the diffusing atom. So the concept is similar, right? Okay, so now you know you have some concept. You can have the concept about what is the interstitial C mechanism. Then next, and also you know, self-interstitial defect play an important role or driving force to drive this diffusion happens. So next I'm going to introduce to you, there are several different types of self-interstitial defect be found in our materials. Let's take a FCC single unit cell as an example. I'm going to show you there are 6 different types or kinds of interstitial defect. Okay, so I use this green circle to represent the interstitial defect atom in FCC. And don't forget, these atoms are the same type of atom with the host atom. So the A is we call octahedral site, right? Because this is FCC structure and this is octahedral site, right? You got the octahedral 1, 2, 3, 4, 5, 6, right? So this 6 atoms form the octahedron. So at the center of octahedron, we call it this atom located at octahedral site. And this is the one we call the tetrahedral. 1, 2, 3, 4, 4. These 4 atoms form the tetrahedron. And at the center of a tetrahedron, we call it this tetrahedral interstitial site. Both of these are self-interstitial defect. Okay? And the third one, actually, if you take a look closely, like C actually is a 110 crowned ion. So what is 110 means? If you try to use the X, Y, Z to label it, and you will find this interstitial defect will form in between these 2 atoms located at the center of the base. And if you try to link these 2 atoms and the directions, that is along 110. So we call this type of self-interstitial defect belongs to 110 crowned ion. ABC actually ABC actually belongs to just there's one atom be inserted into the interstitial site, no matter it's octahedral, tetrahedral, or crowned ion, right? But the DEF is a little bit different because that belongs to, we only have one lattice point, but there are 2 atoms together occupy this only one lattice point. Okay, so for the D, we call it is a 100 split dumbbell. 100 means if you try to link, so there was a lattice point here, right? And there are 2 atoms to co-occupy this lattice point. And if you try to link these atoms, the direction is along 1, 0, 0. So we call this type of interstitial defect as a 1, 0, 0 split dumbbell. And for the E, actually, also we only have 2 atoms share one lattice point, but the direction is not the same with this one, right? You try to link these 2 atoms together, so it belongs to 1, 1, 1 split. So we call it as a 1, 1, 1 split. So the first the direction part usually is describe the direction of this the 2 atoms. If you try to link them with a linker and the direction of this linker. And the F actually is we call a 110 split crowned ion. So also we have 2 atoms occupy one lattice constant, but the long axis you try to use a linker to link these 2 atoms. The direction belongs to 110. We call it as a 110 split crowned ion. Okay, even though we have different type of self-interstitial defect, but don't forget the figures, all these figures looks like, oh, you have sufficient space to insert atoms inside this unit cell. But in real case, as we know, the FCC structure is close packed, right? If you try to insert, for example, if we don't have this one, right? Don't have this atom, and we try to insert 2 atoms to share this point, lattice point, then for sure, and the size will be the same with the host atom. So we want to insert 2 atoms to occupy this lattice point. You can expect this kind of self-interstitial defect will cause very high lattice distortion. So that will result the energy barrier will be higher. For sure, the formation energy is higher as well. So even though we have this 6 different types of self-interstitial defect, but this one, split dumbbell, has the lowest formation energy, which means that they will cause the lowest or least lattice distortion. So based on the lowest formation energy, we have more chance to observe these diffusions happen in our materials. So next following slide, we are going to show you the examples about the interstitial C mechanism. The diffusions happen through interstitial C mechanism, and the case we talk about will be the split dumbbell. So the material structure we choose actually is the same with previous slides FCC, and we have an interstitial mediated self-diffusion happen in FCC. Self-diffusion means we have we insert the host atom. The host atom located at interstitial site. This kind of self-interstitial defect, we call it as a interstitial C mechanism. So we first of all we try to draw 2 FCC structures, and we allow the phase. Because we focus on split dumbbell, right? So we remove these atoms, or you can say that we insert the other atoms, host atoms, to share this lattice point. And based on these figures, and please take a look regarding to the coordination or coordinate axis. This is S, Y, and Z. So based on this, we know, we observe that there are 2 atoms share one lattice point, and the long axis or the linker between these atoms are along 100. So we call it as a 100 split dumbbell defect. SD is an abbreviation of split dumbbell. can consider these two atoms are a group of that. Okay, so the purpose here is we try to formulate the self-diffusivity of this self-diffusivity through this interstitial C mechanism. Okay, so based on the equation we derive from first sections, we need to determine the possible jumping, the coordination number or possible jumping directions, and also formulate the distance r and also f. But for f, this because the atoms can jump to any substitutional site, so f for sure it will be equals, we don't know the f, so we can just in the beginning we just lived here. Okay, but I will explain more later. So let's start from the Z. Because we consider split dumbbell or these two atoms as a group, so we need to consider where is the shortest distance, jumping distance for these groups. Because the upper atom is upper than the lattice point, so the shortest jumping distance will have 4 possible locations, is 1, 2, 3, 4, right? And the upper atoms also have 4 possible jumping locations, is 1, 2, 3, 4, right? Because this location actually is below the lattice point. And for the upper atom, we have 4 chain directions, and the bottom one have 4 also. So 4 plus 4, we got to 8 in total. So why we can directly end it 4 plus 4? Because the jumping mechanism, diffusion mechanism for split dumbbell is either can be like the upper atom jump. Then this, for example, if the atoms jump to number 3 location, then this atom will back to the lattice point, so you can observe the split dumbbell move from this location toward to this direction, this location. And the direction will switch to along the axis will be 0, 0, 1 split dumbbell. So based on this example, you know one of these atoms jump away, then that will cause the diffusion happens, right? So you can directly, so can be this one 4 and this 4, so 4 plus 4 equals to 8. And regarding to the distance, we can use the lattice point. We can measure the lattice point from this lattice point to this lattice point. So got the a divided by 2 square plus a divided by 2 square, and take the root on it. So you got a divided by square root of 2. And as I mentioned before, because this interstitial defect can jump to any substitutional site, so f equals to 1. Okay, and z equals to 8. And if you use the gamma prong, you got the mu times the migration energy, right? And energy Ch4 can be equal to h minus ts. So you delete t term, so you got the temperature independent term and temperature dependent term. So if I want to, then we can easily to formulate the diffusivity of this split dumbbell is just input this information. So you got the gamma r squared divided by 6, and if you use this to substitute r, you got gamma a squared divided by 12. Then you can separate, you can use substitute gamma into 8 gamma prime, so you can get the di, is the diffusivity of this split dumbbell. But don't forget, the purpose here is not the diffusion is due to the diffusing atom. There's the self-interstitial defect nearby the diffusing atom. So the our target is want to calculate the self-diffusivity, right? And this self-diffusivity is through interstitial mechanism, so this dot equals to xi dif. Xi is the fraction of self-interstitial defect, and diffusivity of this interstitial defect times the correlation factor, also not, yeah, the correlation factor f. So this result actually is the same with we learned in vacancy mediated diffusion mechanism, right? For that one is xv dvf, because for sure there's a vacancy nearby, right? And times the vacancy diffusivity you got and times the f. So the idea will be the same, so easy to remember. So what's the xi? Is the formation energy, right? So you use the formation energy, interstitial defect formation, self-interstitial defect formation energy, and diffusivity will be like this one, just copy and times f. So after organize, you can organize the temperature independent term and temperature dependent term, and inside, so independent term will be d0, and the exponential term is a temperature dependent term. And inside the temperature dependent term, the energy part will be included the migration, the self-interstitial defect formation energy, and the interstitial and the migration energy. Okay. Okay. So today just ended here.